Alright guys, so the next planar carbon that we've got to look at is carboxylic acids. So carboxylic acids have the functional group COOH, and the name of them is going to end in oic acid. So we've seen examples of this before, like ethanoic acid. We've mentioned that a lot in acids and bases. And we're just going to go into more of the structure of that now. So what the COOH means is that you've got a carbon that's double bonded to an oxygen. So we've got a carbonyl part, so carbonyl from aldehydes and ketones, and we've got a hydroxyl group on that same carbon, so from our alcohol. And when we put those together, we write it as COOH, which is our carboxylic acid group. And again, this R over here just represents the rest of the carbon chain. So some examples: methanoic acid. So again, the naming for these is fairly straightforward. Methan means that there's one carbon single bonded to a hydrogen. Oic acid tells you that there's this functional group, OOH. So again, double bonded to the oxygen, just like in aldehydes and ketones, and the same bonding here to the hydroxyl group as in your alcohols. Ethanoic acid, one we've seen plenty of times. To draw that out, eth is two carbons, and telling us that it's singly bonded, and oic acid, we've got that functional group here, the OOH. Propanoic acid, three carbons, carboxyl group at the end of it. This is called a carboxyl group, by the way. And butanoic acid, four carbons in our chain, including, so when you're naming them, you're including the carbon that has the carboxylic acid functional group there. So to name them, count the total number of carbon atoms in the longest chain, including the one in the COOH group. Always count from the carbon atom in the COOH group. So this carbon, the red carbon, is always number one. That becomes more important if we had a chain like the methyl here. If that was to be on this carbon, it would be 3-methyl-butanoic acid. Your numbering starts from the carboxylic acid group. Occurrences and uses: methanoic acid is found in the sting of ants and nettles. Ethanoic acid we've seen in vinegar, and it's also used in the manufacture of cellulose acetate. Propanoic acid and benzoic acid, and their salts are used as food preservatives. Not much else to say on that, I don't think. Just to say that cellulose acetate, there is the importance of that is that it's used in varnishes, lacquers and rayon, if any of you are into photography as well. So that's our occurrence and uses. Physical properties: methanoic and ethanoic acids are liquids, while propanoic acid and butanoic acid are solids. And you only need to know up as far as C4 here for these ones. So 4 carbons. So the first two are liquids, second two are solids. Short chain carboxylic acids are soluble in water due to the polar COOH group. So again, same as all of the other compounds we've been looking at. Short ones are soluble in water. The longer they get, the solubility decreases in water because of the non-polar part of the molecule kind of taking over and outweighing that. So short chain ones are soluble in water, longer chain ones are not. They're soluble in non-polar solvents such as cyclohexane. The boiling points of carboxylic acids are higher than their corresponding alcohols. So we're comparing them to alcohols because of that hydroxyl group in there. This is because carboxylic acids form something called a dimer, where two carboxylic acid molecules are held together by 2 hydrogen bonds. This is possible due to the polarity in both the carbonyl group and the hydroxyl group in the carboxylic acid molecule. So what does that mean? That means that, so whichever one of these, I've put in the 2 diagrams here for you to have a look at, whichever one you find more helpful. So in your carboxylic acid group, looking at this one, you've got your carbon, your 2 oxygens and the hydrogen. There's going to be polarity here. The oxygen here is going to be slightly negative, and that can form a hydrogen bond with the hydrogen on the hydroxyl group on the other atom, or in the other molecule, sorry. And then the delta positive hydrogen on this one can form a hydrogen bond to the slightly negative oxygen on the other molecule. So you've got 2 hydrogen bonds there holding the molecules together. Therefore, we have, oh sorry, went too far. We have high boiling points due to that, because it takes a lot more energy to break those hydrogen bonds. That's the end of our carboxylic acids. So now we'll move on to the last one we need to have a look at, which is esters. Esters have the functional group RCOOR. So if you look at that here, this is very, very similar to the carboxylic acid functional group. You've got your carbonyl here, your carbon attached double bonded to oxygen. But instead, on the hydroxyl group, we don't have a hydroxyl group anymore. The hydrogen that was here has been replaced with another carbon chain. So it's RCOOR. So it's basically like a carboxylic acid group, but it's in between 2 carbons in the chain. And how we produce that, and this is something we'll look further into in the next chapter as well, but it's important to note now so that you understand the naming of esters. To make an ester, it's done by reacting an alcohol with a carboxylic acid. So this reaction is called a condensation reaction because we're losing water, so condensation produces water. A condensation reaction is a chemical reaction in which 2 molecules combine to form a larger molecule, so alcohol and carboxylic acid forming a larger molecule, which is the ester, with the loss of a small molecule such as water, so we're losing water there. We're not going to go into the actual equation at the moment, we're just looking at that now so that we understand the naming. So the first part of the ester name comes from the parent alcohol. So if we take this example, we've got ethanoic acid and methanol reacting together. So the first part of the name of our ester, the first part of the name comes from the alcohol, so it's going to be from methanol, but we change the anol to il, so it's going to be methyl. So we're calling this similar to how we would name a side chain. The second part of the name comes from the parent acid, with the oic acid changed to O8. So ethanoic acid, the ending changes to O8. So you identify your esters from their functional group, the 2 oxygens in the middle, or from the name, it ends in O8. So just to point that out again, the methyl ethanoate name, methyl, tells me that methanol was used to create it, and ethanoate tells me that it was ethanoic acid reacting with the methanol. Just some diagrams here that you can pause and have a look at just to see the structure. Methyl methanoate, so we've got the methyl bit here and the methanoate bit over here. Another example for you, and you only need to know up as far as C4, so the ones with 4 carbons in them. So this is one example of that. You can see we've got 2, 3, 4 carbons here, and this is ethyl over here, ethanoate over here. And the other one is methyl. I've spelt that wrong, I've left out the L there. So methyl propanoate is the other one. So meth would be 1 carbon, prop would be 3, and that adds up to 4. So they are the examples that you need to know for esters. Some physical properties: they are liquids, the 4 that we're looking at, or up as far as C4. They're liquid, their boiling points are higher than the corresponding alkanes, but lower than the corresponding alcohols. Lower members of the ester family are volatile liquids with a fruity smell. Lower members are soluble in water, larger members are soluble in non-polar solvents such as cycloalkane. or cyclohexane, sorry. And then this is just going through the reason for that again, and it's because the carbon chain gets longer, that's non-polar, and that's going to compromise the polarity. Some occurrences and uses here, they occur naturally in fruits and flowers, giving them their flavours and smells. Fats and oils are esters as well. They're long chain carboxylic acids converted into esters. Ethyl ethanoate that we mentioned earlier on is used as a solvent for inks and paints. And polyester, something I'm sure you've all heard of or seen inside in pennies. Millions of ester molecules linked together. So that is the end of our planar carbon compounds part of this chapter. So just remember to check out Microsoft Teams to see your work that you need to do following this.